And we're live. So last time we were building volume by cross sections by stacking a bunch of 2D areas on top of each other. This time we're doing kind of the same thing, um, in that we're still ultimately building three-dimensional shapes. But instead of just stacking a bunch of two-dimensional shapes on top of each other, we're going to be rotating an infinitely small two-dimensional shape about an axis, and then stacking those rotations on top of each other to create our 3D shape. So this is called dis method, um, which is all we'll be working with today. I'm not going to worry about what's happening on the right side of this slide at all. But in dis method, we're going to continuously spin these two-dimensional cross sections about some sort of axis of rotation, in this case the x-axis for the picture that I'm showing right now. And then use those cross sections to build a three-dimensional shape like this. Okay, if you wanted to create a hollow shape, we can do this twice. So taking a single radius, so r1 is your distance from your outermost function to your axis of rotation, and spinning that around to create a two-dimensional circle, and then cutting out r2, your distance from your axis to your innermost function, as a second circle. And then when you keep stacking larger circles with smaller cutouts on top of each other, you'll end up with a smooth three-dimensional shape. Okay, any questions just on the idea of what we're doing right now? Okay, this will make a lot more sense when I jump into examples, so let me do that. Okay, I do have writing on here from the last class, and then I think will make this go a little bit faster, but that'll allow us to do a couple more examples towards the end. So here I've got, zoom out so we can see the whole problem. We are finding the volume of the solid that happens when we revolve this area in blue about the x-axis, which means I'm going to take this two-dimensional blue area here and spin it about the x-axis in order to create this three-dimensional shape, a shape that looks kind of like an acorn or a bullet. So in order to do it, I'm going to create these two-dimensional cross-sections that are circles or disks. Each one of these disks that I'll spin around the axis has a radius, which is my distance from the axis itself to the outermost function. So in this case right now, our radius is from here at the axis to here at the top of our function. So I can say that that radius right now is equal to the y value. Whatever the y value of this y equals the square root of x is, should give us the distance for our radius here. Okay, then to give this disk depth, we can give it an infinitely small depth here, shown in purple as dx. So that means the area of this disk would be the yellow part, which would be pi r squared. And since our radius is y, this would be pi y squared for the area of each of these disks. Okay, here it is again. And we've got one disk here. Our two-dimensional cross-section that we got by spinning this line here in black about the x-axis. Okay, if I wanted to make this three-dimensional, Then we should have an infinitely small change in x. Which we would also spin about the axis of rotation. Looking something like this. And then if we keep doing that all the way down the function, so stacking more and more and more of these disks together, we'll end up with a solid three-dimensional shape. So we'll end up with an acorn-like three-dimensional shape. So in order to take this yellow area and make it into a volume, I would have to multiply by the height, which is my change in x, my depth. So I could say that our volume is equal to my area, which we said was pi r squared, where our radius is our y value right now, my distance from y equals 0 to our function y equals square root x. If I take that area and I multiply by our change in x, then I'll end up with a three-dimensional shape instead of a two-dimensional shape, which is a volume. And I'm going to keep doing that, area times dx, for every possible x value that I could plug in from 0 to 4. So I'll end up with infinitely many of these small disks. Since we were told our y value is the square root of x, y is the square root of x is our original function, I can pull out this pi because that's a constant, and then multiply by my radius squared. My radius is square root x since that's my y value, so when I square that square root, my square root will go away. So I'm left with pi times the integral from 0 to 4 of x dx. If we integrate x, we get x squared over 2. Multiply again by the constant, gets pi x squared over 2, and then I'm going to plug in my upper bound and subtract my lower bound to get my final answer. So if I do, I end up with 8 pi. 8 pi is the volume of the acorn-like shape that we've created by stacking a bunch of these two-dimensional disks on top of each other. Okay, since this two-dimensional disk is the hard part, you guys already know how to integrate. Focus on that one more time. We're going to create infinitely many of these two-dimensional disks that we're spinning about our axis of rotation, starting at x equals 0, and then moving all the way over to the end. So we're just continuously stacking more and more and more of these disks together in order to make our three-dimensional shape. And eventually we'll end up with solid. All right, any questions on what we did? Okay. Check, make sure that's not you guys. Nope. I think I'm going to redo this one from the top, and then have you guys help me out once we get to the integrals. So this time I'm going to do the exact same problem. We are going to find the volume. Resulting from revolving the area enclosed by y equals the square root of x. x equals 0 and x equals 4. About the line y equals, I'll say 6. Okay, so I'm going to draw this out. It's going to look something like this. I've got our function, which I'll do here in blue, which is y equals the square root of x. And we are bounded by x equals 0 and x equals 4. And the line y equals 6, which is our axis of rotation, which would be somewhere way up here. Since if I plug in x equals 4 into our y value, my y value is only 2 at that point. So y equals 6 should be well above that. I am going to take this two-dimensional area here and spin it about this line so that will create a three-dimensional shape. Okay, so to do that, I need two things. I need an R1 and an R2. So I'm going to pick a point somewhere in the middle here. I'm going to say here-ish. And we'll get our two radii. I'm going to do my first radii here in purple. Is my distance from the axis of rotation, in this case y equals 6, to the outermost functions, the outermost part of our area. How much is this line? First person of the order, Aileen? What is this distance in purple? Okay, say again. Okay, I'm still not able to hear really. Yeah, Skype, that's I can turn you up. Okay, can you say it one more time? We should not need to see a number right now. Wait, do you need to see a number or do you need to say a number? The answer for this one for how long the purple line is a number.
How long?
Yep. How long is the purple line? Okay, 6 units. And it does not matter where this is. This is still going to be 6 units. Okay, then I'm going to draw one more. Okay, this line here in green is my R2. How much would the green distance be? Okay, the green distance is not a number this time, but a function. Perfect. 6 minus root x. Okay, that's the hard part. Um, so what we're going to do is I'm going to take these two radii and we're going to use them to create a disk that we will end up spinning about our axis of rotation. So that's going to look something like this. Mm. Okay, so I'm going to take this this purple radius and spin this about our axis of rotation to create a massive disk here in yellow. So maybe I'll just keep this purple here in purple. Okay, then once we've got our disk here in purple, I'm going to cut out another disk in front of it, which is this radius here in green. Should look something like this. Okay, both of those disks would have an infinitely small width of dx. Should look like this. Again, I'm exaggerating a little bit here because this would be infinitely small, kind of like a sheet of paper. Since we'll want to keep stacking these disks on top of each other again and again and again and again. Okay, and we're spinning about our axis of rotation here in red. Okay, so I've got our radius here for the green disk is R1. And our radius here for the purple disk is R2. And our infinitely small change in x is dx. I guess that means I can leave this part down here in yellow. Okay. Oops. R1, R2. Okay, any questions on what we did with our picture so far? Okay, so we're always going to have these disks. You're always going to have at least one radius. If you're creating a hollow shape, then you'll have two. So your first radius will always be the distance from the axis of rotation to the outermost function. Similarly, your R2 will always be the distance to the innermost function from the axis of rotation. Which for us, and then gave us R1 is 6, and R2 is 6 minus root x. Okay, so now I just need to make this into a volume. So next on the order is Jenna. Jenna, each one of these two-dimensional disks, in purple and in green for our picture, should have an area. What would the area of the purple disk be?
Pi r squared.
Okay, pi, I've got two radii. Pi r1 squared or r2 squared?
R1 squared.
R1 squared, okay. So for us, because R1 is 6, that would be pi times 6 squared, or 36 pi. Okay, that disk does not change no matter where we are as we go through this yellow area. So that does not change based on our x value. But our second area will. A2. Jenna, what's our second area?
Pi r2 squared.
Pi r2 squared. What happens if I square this?
Um, 36 minus 12 root x plus x.
Perfect. Okay, jumping over to Kelly. See if I can zoom out well enough to get their picture still in here. That's the best I can do, I think. So Kelly, I want to take this information and turn them into volumes. So my total volume should be what? Kelly, can you hear me? Okay, nothing from Kelly yet. I'm gonna jump over to Sarah next then. Okay, so Sarah, we've got this A1 and A2 here, area of the purple disk, area of the green disk. I want to take them and turn them into volumes. What would the volume of the of the three-dimensional purple disk be? Okay, from last class, if we had a two-dimensional area, we could multiply that by the depth, and we'd be able to get a volume. So what would the volume of the first disk be in purple? Okay, first I'm moving from 0 to 4, but then I need to multiply my area times my depth. What's the area of the purple disk? (36 pi). And what's the depth of the purple disk? Got 36 pi times, I need one more dimension. Not 6. So this is how deep that this two-dimensional purple disk goes. So here in, I guess this is a little bit more pinkish, but this depth is my infinitely small dx. So if I multiply 36 pi times dx, I should be able to get a three-dimensional volume. Okay, that would be the volume of my first disk is pi times r1 squared. Okay, then I want to be able to subtract the volume of my second disk, which would be, oops, I lost my pi in this actually. Pi r squared, this part's the r squared, but I didn't multiply by the pi, so I've got my area 1 here, minus my area 2. 36 minus 12 root x plus x times pi, also in terms of x. I guess I'll write that out for now. dx, and this is 36 pi came from my area of the purple disk. Okay, so I'm going to simplify just a little bit. I've got a pi in both terms. That's a constant, and I can pull that out. This is my total volume now. I've got, our total volume is pi times the integral from 0 to 4 of 36 pi minus 36 minus 12 root x plus x times dx. So I factored out my dx. So that tells me what variable I'm integrating in terms of. I'm integrating in terms of x. I factored out my pi because I had one constant pi in both terms. And this is really r1 squared minus r2 squared from a start point to an end point, which actually works for our general formula. The volume of any shape we want to revolve would be equal to pi times the integral from a start point A to an end point B of r1 squared minus r2 squared in terms of x. Anytime you see an integral and you see a d some variable afterwards, you are actually distributing that into every term. So you don't need to write these parentheses. They're kind of understood as long as you're integrating. You'll run to the end of your integral when you hit your d, whatever your variable is. But if you want to write like this, you can, just to show that you're distributing. If you don't, it'll be assumed you're still distributing though, since you have to have a d some variable for your integral. Okay, where r1 is your distance from outermost function to the axis. R2 is your distance from the innermost function to the axis. A is your start point. And B is the end point. Okay, I guess we say dx is your depth, which makes this three-dimensional. Okay, but what this formula really does is it takes the area of disk 1, pi r1 squared, and subtracts the area of disk 2, pi r2 squared, but then multiplies both by dx to make it a three-dimensional shape. So just like our picture here. We've got one large disk in purple with a depth in pink. And I'm going to cut out a smaller disk in green, which has the same depth in pink, to make the disk hollow. If I keep stacking every possible disk from x equals 0 to x equals 4, we'll end up with a three-dimensional shape. Okay, the outside of that shape would look like a cylinder, but the inside of that shape would be curved. So kind of like a cone almost. Okay, any questions on what we did? Okay, I think I'm going to solve the rest of this. So we'll get the actual volume. Yeah, we've got time. Okay, we've got 36. Oops, I made another mistake. I have a pi and a pi. I pulled that pi out. I actually don't have a pi in here anymore. Okay, who's next? Kenichi?
Hello?
Hey, I'm going to work out this integral. So before I do, is there anything in there that can cancel?
You can cancel 36 minus 36.
Perfect. So this will become our
0.
Okay, so 36 minus 36 is 0. I need to distribute this negative in. So what do we have left?
So positive 12 square root x
Okay, I'm gonna write.
minus x.
Okay, perfect. I'm gonna write that as 12x to the 1/2 power, which is the same thing as the square
Yes.
root, and that'll help us with our integral next. Okay,
Mhm.
and then I need to integrate this. So I'm gonna add 1 to the power and divide by the new power for every term. What's gonna happen when we integrate?
We should add 1 power to each, right?
Yep.
Um, wait. Mm, 2.
What's 1/2
Uh,
plus?
1/2 plus 1
Mhm.
is 1/2.
1/2
No,
plus
no, 3/2.
3/2. Okay, and then I'm going to divide by the new power, so I'm dividing by 3/2. Okay, how about this one?
That's gonna be just only x.
Add 1 to the
Because you're
power,
gonna add. Oh no, no, I mean 2
okay,
square.
x squared over 2. Okay,
Mhm.
and then we've got our upper bound and our lower bound. Oops, 4. So I'm going from 0 to 4. Okay, jump to the next person. We've got okay, I've got Tommy in there as well. So Tommy, what's going to happen when I divide by this fraction? So
Um, 12x? No way.
okay, if we divide by a fraction, we can flip and multiply. So 12x to the 3/2 power divided by 3/2 is the same thing as 12x to the 3/2 power times 2/3.
Yeah.
Okay, if I multiply this out, what will I have left?
8x or 2/3.
Okay, 8x to the 3/2 power, that's a language difference, that's okay. Minus x squared over
Oh,
2 from 0 to 4, okay? So I'm going to
yeah.
plug in my upper bound and subtract my lower bound. So the way this works is x to the m over n power is the same thing as the nth root of x to the m power, right? So if I plug in 4 right now, then this will be the square root of 4 cubed. Okay, what's going to happen?
It's still me?
Yep, still you.
Oh,
So what's the square root of 4?
um, uh, I don't think so. I know this.
Okay, so square root of 4 is 2, and then I'm going to cube that.
Yeah.
So that'll be 2 cubed. Or 2 times 2 times
2,
2.
2.
Yep. What is 2 cubed?
4. Oh, I mean 8.
8? Okay, so I've got 8 times 8.
-4.
Yep, 8 times 8 minus 4. Okay, so what should this be?
Um, 60.
60, and then I've got the pi on the outside, so that's 60 times pi.
Oh,
Awesome. All right. Any questions on our work here for the volume? Okay, I'm not as concerned about the integration part as I am about the setup. Let me do one more here, because I think we've got time for at least one more. And we'll stop there. So I've got a picture here from Desmos. And I want to find the volume. From rotating the area bounded by y equals secant x, y equals 0, x equals negative pi over 6, and x equals negative pi, or positive pi over 3. About the line y equals negative 1. So I'm going to take this yellow area and I'm going to spin it about the blue line. And then I want to know how much volume would that yellow area have passed through if I spun it around the blue space. Okay, I'm back to the top of the order. Aileen, I need an R1 to start out with, which is my distance from the axis of rotation to the outermost function. Okay, right now we were told our axis of rotation. Our axis of rotation just means the line you're spinning around. So in this case, that's the blue line. Okay, say one more time. Negative 1. Negative 1 is the axis of rotation. So I want to know our R1, which is my distance from the axis of rotation to the outermost function. So in this case, outermost function would be the red line. What is this distance? Not just 2. Okay, so I'm not really looking for a number. I'm looking for a formula, since this distance is going to change based on our x value. It has to do with secant x and minus 1. What's the difference between them, though? I'll try again. So just secant would give you this distance. Huh? If I doubled it, I would end up with going all the way down to here. So secant x tells me how far above 0 I am. How much further do I need to go in order to get to the blue line? Um, this blue line is my distance from y equals 0, that's my black line, to y equals -1 here in blue. So how much is this light blue line? Um, just 1. I'm looking for a distance. Okay, so if this blue line is 1, and this red line is we said secant of x, then what's the total distance here in green? 1 plus secant x. Okay, an easier way to do that, if I'm going to put this all together, is if I'm looking for the difference between the distance between two y values, I can subtract them. So this would be the secant of x minus -1 would give me the secant x plus 1. So that's the difference in my y values. And that ends up adding because this y equals -1 is on the other side of y equals 0. If I was trying to get to y equals 1/2 instead, then I would do secant x minus 1/2 to get the distance between them. And the formula would still work. Okay, that's the hard part. It's actually the hardest part of all of this so far. Any questions on how we got our radius? Okay, next in the order is Jana. Jana, I also need an R2, which is my distance from the inside of this area to the axis of rotation. What is our R2?
-1.
It should be a distance, though. Y equals -1 is the axis of rotation. I want the distance from the axis of rotation to the innermost function. So this is the area where I'm cutting off. Then I want this distance. How much is this distance? Y equals 0 is the bottom of our area that we want to spin. I want the distance between y equals 0, the bottom of the area, and the axis of rotation at y equals -1.
Don't know.
No. Okay, I'm going to jump over to somebody for help. Kelly, are you there yet?
Yeah.
Okay. What's my distance between the axis of rotation and the bottom of our area?
I don't know.
Okay, right now our axis of rotation is here at y equals -1. And our area is bounded by the x-axis, which is here at y equals 0. So what's the distance between them?
1.
Just 1. Okay, so R1 is always your distance to the outermost functions. That's the part of your area that's the furthest away from your axis of rotation, here in green. In this case is secant x plus 1. R2 is always your distance to your innermost function, to the axis of rotations. That's the the closest edge of the area to our axis of rotation would be from y equals 0 to y equals -1 is a distance of 1. Okay, then I'm going to take those radii and we'll plug them into our formula. So our volume is pi times the integral from a start point to an end point of r1 squared minus r2 squared dx. Okay, which will essentially be doing this. I'm going to take this radius here in green and use it to spin a disk about our axis of rotation. Okay, once we've got that disk, which will have an infinitely small change in x, then I'm going to take that disk here in green and we're going to cut out a smaller disk in blue. To make the hollow part of our shape. Okay, so right now I've got our larger disk in green that we've cut. I'm going to take that solid and we'll do our radius here in blue. And use that to cut out a smaller disk. This will be symmetrical. Here to here. There we go. So that our shape ends up being hollow. Okay, any questions on what we've done so far? All right. So I'm going to plug this in. I've got the area of disk 1, that's the area in green, is pi r1 squared. So that will be, our volume is equal to pi times the integral from start point and end point. This area starts at negative pi 6 and ends at pi thirds. Okay, my first radius is here in green. Secant x plus 1. I'll need to square that. Minus our second radius here in blue. Is 1. Okay, times our depth in purple is dx. All right, taking a look at the picture. Any questions on how we set this up? All right, if we spin this shape about the axis of rotation, you're going to end up with a shape that looks a little bit like an hourglass with a cylindrical hole in it. Because we're cutting out this hollow shape in the middle. Okay, so let's finish this off and we'll integrate. Next in the order is Sarah. Sarah, what's going to happen when I square this? Okay, so I've got secant x plus 1 times secant x plus 1. So you've got the first part, secant squared x plus... Okay, if I square this, what's going to happen? Two secant x, okay, plus... Okay, we had secant times secant is secant squared, plus secant times 1 plus secant times 1, okay, is 2 secant x, and then plus 1 times 1 is our last term. For plus 1. And then I've got the minus 1 from this side, dx. Okay, any questions on what we did here? Alright, I'm going to jump over to Kenichi on Skype. Kenichi, if I want to integrate secant squared, what's going to happen? Do I still have Kenichi? Yes. Okay, Kenichi. If I want to integrate secant squared, what will happen?
So you add 1 to the power, right?
So for this, we're just working backwards. So what function
Okay.
could we derive in order to get secant squared?
Cosecant.
If I derive cosecant, I get negative cosecant cotangent.
Oh no. Okay. Um. What if you try? Oh, if you drive. Wait, secant? No. If you drive cotangent? Oh no.
If I derive cotangent, I get negative cosecant squared. So we're a little bit closer.
Tangent.
Tangent, there we go. Okay. So if I derive tangent, I get secant squared, so working backwards.
Uh-huh. And then.
Okay, tangent. My 1 and my negative 1 would cancel.
Okay, yes.
Okay. Then
Mhm.
we actually haven't done this one yet, so we don't know this one yet. But Got my 2 as a constant. If I integrate secant, I'll end up with the natural log of tangent plus secant,
Okay.
which I don't expect us to know yet, but this is just me picking a problem off the top of our head that we haven't actually learned how to integrate yet. But and then the 1 minus 1 is going to cancel.
Mm-hmm.
Okay, so this is from negative pi 6 to positive pi
Mhm.
thirds. Okay. So then I need to plug in these unit circle values to get our
Mm-hmm.
final answer,
Okay.
which I may need another page for. Okay, so I'm going to jump over to Tommy. Tommy, what's the tangent at pi thirds?
Tangent of pi third.
So here's pi thirds. It's got a long side and a short side for its y value and its x value. Short sides are always 1/2. Long sides are always root 3 over 2. Tangent is y over x. So what's the tangent at pi thirds? I might do this.
2 root 3 over 2.
So this is going to be root 3 over 2 divided by 1/2.
Isn't it just root 3?
Yes. Root 3. Okay, plus the natural log of, and you already told me what the tangent of pi thirds was, that's root 3, plus the secant at pi thirds. Secant is 1 over cosine. Secant x is another variable, theta. The secant of an angle is 1 over x. Okay, so what should the secant be in this case?
Just 1.5.
So this will be 1 over 1/2.
Yeah.
Okay, what is 1 divided by 1/2?
1 divided by 1/2.
Mm-hmm.
Isn't it just like 1 over 2?
This is 1 over 1 over 2. If I have one sheet of paper and I split it in halves, how many halves do you have?
2.
2. 1 divided into 1/2 pieces will give you 2 pieces total. If you divide by a fraction, you can flip and multiply. So this is the same thing as 1 times 2 over 1 is 2. Okay, so that's my upper bound. I'm going to jump over to, I'm back to Aileen again for my lower bound. So Aileen, I need to do the same thing, but at negative pi 6. So I'm going to draw our picture again. I probably should have left that for our notes. Okay, I'm going to leave that for our notes, actually. This is pi thirds. This is a short side, which is 1/2. This is a long side, which would be root 3 over 2. At negative pi 6. I'm exaggerating. There we go. Our long side is root 3 over 2, and our short side is negative 1/2. Our magnitudes are the same, but our y value is negative because we went down, and this is at negative pi 6. Okay, so I need the same thing. What would the tangent be And what would the secant be at pi 6? I'm sorry, negative pi 6. Okay, I couldn't quite hear. Can you say it one more time? Okay, perfect. So negative root 3 over 3. That was negative 1/2 divided by root 3 over 2. Would give me negative 1 over root 3, which we could rationalize to negative root 3 over 3. Okay, and then what about the secant? 2 root 3 over 3. Okay, perfect. That was 1 divided by my x value. My x value is root 3 over 2, so if I have 1 over that fraction, I'll flip it. Will give me 2 over root 3, and I can rationalize to 2 root 3 over 3. Okay, so now I'm going to plug those in to our formula up here. So I need the tangent, which we said was negative root 3 over 3, plus 2, I didn't have a 2, 2 times my natural log of the tangent of x plus the secant of x. So that's the tangent of x, negative root 3 over 3 plus the secant of x, 2 root 3 over 3. Should give you my answer. All right. So we'll simplify what we can. This is the same thing as pi times 3 root 3 over 3 plus 2 natural log of root 3 plus 2 minus negative, so that's plus root 3 over 3 minus positive minus 2 natural log of negative root 3 over 3 plus 2 root 3 over 3 is root 3 over 3. Or pi times 3 root 3 over 3 plus 1 root 3 over 3 is 4 root 3 over 3 plus 2 natural log of root 3 plus 2 minus 2 natural log of root 3 over 3. I could use properties of logarithms to combine this. I'm okay if you leave it just like this, though. Any questions on what we did? Erase this line just to make sure that's not in the way. Okay. I am way over time and I apologize. So I'm going to leave a couple more examples from the last class in the WeChat group. The homework this time is easier than the stuff that we did in class today. So I was trying to give problems that have everything about all the problems in one set. But the homework is easier than what we did. So homework is up on WeChat and actually already up on course sites as well. And I'll repost really quick. Okay, I should release you guys while we're here since we're set too. So thank you guys so much for coming. I'm sorry to keep you over time as much as I have. I will see you again on Friday.
Bye.
Bye bye.
Goodbye.
Have a good day.
You too.